that's me. Here is my email address. So note it, and if you want to have the slides, I will send it to you. My name is Heinz Renner. I'm working for Linsize for many years, and I'm responsible for the sales and the application support in Germany, Austria, and Switzerland. Today, our topic will be the curing in thermal analysis. The focus today will be on two measurement methods with which the whole curing process can be analyzed. The first one, it's called the Dielectrical analysis, DEA, and the second one, which we will see in detail, is the dynamic scanning calorimetry, or short DSC. Let's start at first with some basics about polymer curing before we go into the measurement techniques to analyze the processes. Curing, what does that mean? It is cross-linking of polymer chains to form a network, like illustrated here. There are chains, polymer chains, or at the beginning, monomers, which form polymer chains, and then cross-linking occurs to form a network. The amount of these links between the polymer chains are important for the material properties, for example, the mechanical properties or adhesive properties and so on. The degree of cure is a measure for the number of the crosslinks, and we can measure that. We will see later on. There are many ways to form a polymer network. A broad variety of curing mechanism exists. One example is illustrated here. It shows an acrylate with photosensitive groups, the blue circles here. And if you irritate these blue circles or these photolabile groups with UV light, for example, they form radicals and react with each other, and they are forming chemical bonds. Another possibility to form a polymer network is shown here. It's a reaction of functional groups. In this example, an epoxy group and an amine group, to form here chains and networks. And these kind of reactions are observed in two-component resins, for example. Typical materials which can form polymer networks are, maybe you know that, or you work in these fields, are epoxies, acrylics, polyurethanes, polyesters, polystyrenes, polyimides and amides, bulk and sheet molding compounds, paints, coatings, oils, and some more. If you are in charge with one or more of the shown applications here on that list, then you are right here in this webinar. This could probably give you some helpful input. For example, if you make formulations or investigate reaction rate studies, of course, cure and process development, UV cures, and what is listed here. So this is the topic of our webinar today. Our customers using the dielectrical analysis, DEA and DSC, which is used to investigate curing polymers, are mainly manufacturers of raw resins and raw materials, the suppliers of the monomers, resins, catalysts, supplier of adhesives, paints and coatings, then manufacturers of prepregs, these are impregnated composites, and manufacturer of composite end products, which are used in aircrafts, automobiles, electronics, consumer products, and more. But how to analyze the curing process and cured materials? I will show you a common approach. There are for sure other approaches to do that, but it has turned out the last decades, I would say, that this approach is a good one to completely analyze and investigate the curing process and the cured materials. This figure here shows a typical two-component epoxy, which is mixed in a first stage. Then in the second stage, the materials react. It comes to the cure process. And after a while, we reach the final cure in the third stage. With the dielectrical analysis, DEA, you usually investigate the stage 1 and stage 2. So the curing process itself. With the DSC, you look more on the final product, which is cured, which is at the end of the reaction. And you are investigating glass transitions and maybe post-curing effects. And that is the reason why DEA and DSC are commonly used in the field of polymer cure. They are complementary methods. So let's start with the dielectrical analysis. Our company, Linzais in Germany, and Lambient work together in that field. So Lambient Technologies is located in Cambridge, Massachusetts, in the US. And it was initially in the early 80s a spin-off of the MIT, the Massachusetts Institute of Technology. And the people from Lambient invented in the early 80s the measurement method DEA as a thermoanalytical method. The most DEA instruments in the market are Lambient instruments, which have, I would say, the highest technical level in sensors and electronics. So dielectrical analysis is an established technique to monitor curing. Many people or most people in that field know the DSC, differential scanning calorimetry, but not so many people know the dielectrical analysis. I personally think the reason for that is that maybe the theory behind is a little bit more complicated, but once you know what's going on and you understood to measure and interpret the data, then the dielectrical analysis, it's perfect to monitor curing. It's the only measurement technique which shows you the curing process itself, and it shows you that the curing reaction completely from the beginning to the end. With other techniques like rheology or DMA, dynamic mechanical analysis, it is not possible. The measurements are done with sensors, we will see later on, and the measurements are in situ measurements, and we have here electrical measurements, and as a result of our measurement, we get two figures, the permittivity and the conductivity of the sample. And the permittivity, it is due to the rotation of dipoles in the sample. So functional groups, for example, they are dipoles and they move in the electrical field which you apply. The resistivity, on the other hand, is due to the movement of mobile ions. And that is what we want to measure at the end of the day, because with the resistivity, we see the stage of the curing process. When we look on an electrical model, then we have these two effects illustrated here. So we have here two electrodes. We apply an alternating voltage, an excitation voltage, and as a result, we obtain also an alternating current. And the ions which are in your sample move to the electrode with the opposite charge, like illustrated here. This can be measured, and we measure the conductance of this ion movement. The second process which we have in our sample are, so we have dipoles, and they orient in the electric field. And when we look here on the next slide, then we can look on, for example, a parallel plate geometry, and we apply this sinusoidal voltage, and then we calculate here, or we, in the electrical model, we use here a capacitance and a conductance element. And important for the measurements or for the setup here is the area of the electrodes and the distance between the two electrodes. And the ratio A over D, so the area divided by the distance, it's a measure of the sensitivity of your setup. So the higher this AD ratio, the better you can, or the more sensitive you can measure the permittivity and the conductivity of your sample. We have, with that setup of a capacitance, we have here the problem that the distance D might change. So your sample is in between these electrodes, and if your sample is shrinking or expanding, then the AD ratio is changing, and this causes uncertainty in the results, in the measurement of the permittivity and the conductivity. For that reason, if such a setup with parallel plates is used in dielectrical analysis, then the delta, that is the phase angle between the excitation voltage and the resulting current. There is a phase shift between these two measures, and this phase angle is called delta, and the tangents delta, when you look on these equations here, the AD ratio and the distance calculate out here. And so for this setup, usually tangents delta is used as a measure, and it is insensitive to the distance. But with that setup, you do not get correctly C and G, and especially the conductance is important to monitor cure. And for that reasons, no parallel plates are used to monitor the cure, but so-called interdigitated sensors, like shown here on that slide. And these are foil sensors usually, so thin foils, Kapton foils, and inside these foils you see these wire structures, and on the left-hand side you have an electrode, and on the right-hand side, and they are interdigitated. And this setup, it's more complicated or more difficult to manufacture, but the big advantage is that it does not depend on pressure expansion or compression of the sample, or any dimensional change of the sample, which will be put on this sensor here. So with that setup, with these foil sensors, it's possible not only to measure this tangents delta, this is phase angle, but also the conductivity and the permittivity of the sample, which we need. A little bit of mathematics, but I do not want to go too deep into the theory, which is not necessary to understand what's going on here. But some equations we have to go through. So when you look here on your input signal, that's a sinusoidal voltage. The result, what you measure, is also a sinusoidal current. And if you divide this excitation voltage by the resulting current, then you get Y, the figure Y. This is called an admittance. And this admittance consists of two parts. It's a complex figure, and it consists of a real part. And in this real part, the conductivity or conductance is included. And on the y-axis, there is the imaginary part, which includes the capacitance or permittivity. From this capacitance, later on, you can calculate the permittivity. So from these data, so y is calculated easily from the raw figures. Then in the next step of the calculation, you divide the capacitance and the conductivity with the AD ratio and the permittivity of vacuum. And then you get the figures which you need at the end. And this is the conductivity and the permittivity. And the conductivity in the most measurements, not this conductivity sigma here, is plotted, but 1 over the conductivity, and this is then called the resistivity. It's inverse proportional to the conductivity. The permittivity, to mention that again, is due to dipole rotations during the measurement, and the conductivity or resistivity is caused by the movement of ions in your sample. And this is what we want to have. And this resistivity or conductivity monitors the cure. There is one more very important fact which you need to know to get good results, is that the resistivity or conductivity consists of two parts. A frequency-dependent part and a frequency-independent part. And we need, for our data interpretation, only the frequency-independent resistivity. So when you measure your sample at different frequencies, at different excitation frequency of the voltage, then you will see that there is a dependence, but there exists some frequencies where the resistivity is not dependent on the frequency. And this figure, the frequency-independent resistivity, is called ion viscosity. And this is very important to understand. The frequency-independent component of the resistivity shows you the stages of your cure. In the next slide, we see a typical measurement with a dielectrical analyzer. Plotted is here the ion viscosity. Here the solid line here. And the dashed line is the mechanical viscosity, which was measured with a rheometer, with an oscillating rheometer. And you see that the mechanical viscosity here corresponds to the resistivity, to the frequency-independent resistivity. And that is the reason why at the beginning of the DEA in the early 80s, the frequency-independent resistivity was called ion viscosity, because it correlates with the mechanical viscosity. And what you can see here in that figure is here, these steps are temperature steps. So at the beginning, you heat up until you have a constant temperature here. The viscosities at the beginning go down because when we look a little bit further in our structure of our material, in this case a thermoset, which forms a network with increasing temperatures. So at the beginning, we have monomers here in our sample, and the ions can move very well within these monomer structure. But then at a certain point, the reaction between the monomer starts and longer chains are formed. And this reaction is exothermic. So heat is evolved and the monomers can move. So there is no bigger obstacles here for the ions. And due to the temperature increase at the beginning of our measurement, the viscosity goes down. But then at the next step of the curing reaction, which is called gelation, that the networking, the link of the chains is starting. And with that gelation, we see a very strong, here it starts with the second temperature increase here. So we see here a strong increase in the mechanical viscosity and also in the ion viscosity. And the mechanical viscosity stops at some point. It cannot be measured anymore because the force of a rheometer is not big enough to measure it here. But with the dielectrical analysis, you can see the whole process of your cure. It's not possible with a rheometer and also with a DMA, which is in fact a rheometer with higher forces. You see only the later part of the reaction. When the later part is shown here, where you have a very dense network with a lot of links. So this could be measured with a DMA, but not with a rheometer. So the only measurement method really on available to monitor the complete curing reaction is a dielectrical analyzer. Here is the correlation between the conductivity with the mechanical viscosity measured with a rheometer, and you see that you have a proportional, in this case inverse proportional correlation, and there is only a scaling factor between the conductivity or resistivity and the viscosity, and that gave the resistivity the name ion viscosity. If it's the frequency dependence is important to realize, to measure good data, to perform good measurements, and with a good result, with a good monitoring of the cure, and to find the correct frequencies for the measurements. It's quite easy. So in a first step, you plot the so-called loss factor. It's it depends on the resistivity, this loss factor, and with that loss factor, the correct frequencies should go down, should be inverse proportional over time. So this 0.1 Hertz, for example, shows a good behavior, as it should be. The 1.0 Hertz also, maybe the 10 Hertz up to here somewhere, but here you have some, it goes into a plateau, which is indicating that this frequency at higher times, at higher curing stages, is already too fast. So then it's too fast for the ions here at a certain point. And then what you see is only the dipole rotations, and they give you no information for, to monitor the cure. So the first information from the loss factors, which you can plot in this multi-frequency measurement, is you can see potential frequencies which are correct. And to make that a little bit more correct, then you plot the resistivity and the frequency independent resistivities overlap over the whole range of measurements. You can see the 10 Hertz curve overlaps until a certain point, and then it's stable. So no overlap anymore with the other lower frequencies. And with 10 Hertz, for example, you can monitor the process in the early stage up to here somewhere, but then it's not reliable anymore. So for this specific sample, it's a polyurethane sample, only the frequencies 0.1 and 1 Hertz are good. With the other ones, with the high frequencies, you get wrong results at the end. And usually, to monitor curing of polymers, you are working in a range between 0.1 and maximum 100 Hertz. You do not need instruments with very high frequencies. That's a waste of money, I would say. It makes no sense. And when we plot only the 0.1 Hertz curve, we see here the curing process. And if from this green line, which is the ion viscosity, when we calculate the first derivative, then this first derivative shows you the speed of reaction, the reaction rate. So we have here a maximum speed at the beginning, and then the speed slows down and is quite slow here at the end, but still continues. So a curing reaction can occur over hours and days until the final cure is reached. So it's important to resume that you realize that for dielectrical analysis, you need the ion viscosity to monitor the curing process. The ion viscosity is the frequency independent part of the resistivity. And the ion viscosity needs to be filtered for correct frequencies. And when you are doing measurements, try to do multi-frequency measurements and filter out the correct ones. So this was the basic theory of dielectrical analysis. Now I will show you how the instruments look like. Dielectrical analyzers are small tabletop instruments with a small electronic box. Then it's the instruments are controlled from a computer or laptop, and there are various instrument models available. It depends a little bit of the speed of your reaction. We have high-speed instruments, and we have special instruments which are suitable for UV curing materials. And we have instruments, when you look on the rear side, there are channels, call it channel. You can build in here more than one channel. In one channel, you can connect a sensor. We will see later on that we need to measure with sensors and a thermocouple to measure the temperature. And you can, with this example here, you have 4 channels, so you can at the same time measure with 4 sensors, and you can scale that up. I will show you later on some more examples. The sensor technology which we are using is a 2-wire connection sensor, shown here on the left-hand side. The other possibility would be a 4-wire connection. The 2-wire connection has some benefits, but it's necessary to put in some very low current so we are using an input current of only 8 nanoampere, and this allows us this 2-wire technology, and this has some price advantages. The 4 wires are much higher in price, and the bonding here of reusable sensors, it's much easier here with 2 wires. The 4-wire are not really needed. They have their advantages to suppress noise, but only this is useful for low resistances below 10 ohm. But what we are measuring in curing processes, we are measuring resistances of 10,000 ohm and more. So there is no need for a 4-wire connection. There are a lot of accessories available, like parallel plate test cells. The sample is placed between here the plates and also the sensor, and then you can apply pressure. You can measure that pressure. You can heat up with that test fixture, and there is an ASTM norm for testing solids with that parallel test plate test fixture. Then we have some presses, small presses, which can anyway apply high loads up to 900 kilogram, which is quite big force. So the pressure on the sample can be adjusted to high pressures because we are using small areas here with our sensors in the millimeter or centimeter range. And these presses are used or necessary to investigate the curing of, for example, sheet or bulk molding compounds and other samples. The sensors itself, there are various sensors, disposable ones, shown like here. So thin foils in which the wire structures are. This example is a so-called Varicon disposable sensor. You can use the whole surface here. Then you have the highest sensitivity, the AD, so the surface over the distance ratio of these interdigited electrodes inside here is the highest with 160. That's quite high for the electrical analysis. But if you have only small samples, which do not cover the whole sensor, you can cut here this part and also the other part here, and then you can measure only on that small part. You are losing sensitivity, but you can change here the sample size with these sensors. We have only also mini Varicon sensors. They are inexpensive, quite small, 3.8 centimeters, so 38 millimeter length. They can be operated up to 350 degrees Celsius. They have a lower AD ratio compared to the Varicon, but for the most curing processes, they are good enough. Then if measurements in tools, like in this plate or in molds, are done, then reusable sensors like these Keramicomp sensors can be installed in the tool, or in this example in a plate. The sensor can be operated up to 250 degrees Celsius. It's from stainless steel, and a thermocouple is also included. So it measures the electrical properties and also the temperature. Then we can offer also to customers which have big samples and customers who want to monitor, for example, the curing during the manufacturing process. Then we can offer so-called distributed DEA. So it's a network of DEA channels which are controlled over a device, a central device here. And in this example, a turbine, a wind turbine, a rotor blade is shown. And these blades are manufactured in a mold. And it's important to monitor the curing process to the final stage. And it's important that on every point here on this blade, you have a complete curing. And in the past, it was waited a couple of days until the reaction was finished, and then the blade was replaced with another one. But with the dielectrical analysis, you have a much higher throughput because the reaction itself, you can replace the blade in manufacturing after a couple of hours. And the dielectrical analysis shows you exactly the time when it can be taken out of the mold and a new one can be manufactured. Then also very interesting is the measuring of the dielectrical analysis with UV light for UV curing samples like UV curing acrylates adhesives. The experimental setup is shown in that figure here. At the end of a light guide, a so-called collimator is attached, which concentrates the UV light and projects it onto a platform. And on that platform, there is the sensor, this orange one here, and on the sensor is your sample. You can change the distance of the UV light source, and you can change also the intensity, of course, of the UV light. Next to your sensor, you can place a thermocouple to monitor not only the ion viscosity, which shows you the curing stage, but also the temperature evolved in the reaction. A typical measurement example shows an acrylate adhesive. So you have here a UV exposure time of 1 second. You can see here the time. The green curve is the ion viscosity, and the red curve is the temperature. And during the exposure with UV light, the curve already gets up, and then the curing reaction takes place until, after about 60, 70 seconds, the sample is almost already cured or completely cured. You can do multiple exposures with different distances. Here is an example. The upper curve was with a small distance of 20 centimeters of the light source to the sample. Then only one UV light exposure is necessary to cure the sample completely. When you change the distance to longer distances, you can see that one exposure, it's not enough. You do not reach the final cure. You need another exposure for this distance here, 38 centimeters. And for higher distances, you need even 3 or more exposures of with UV light. Here is an example, also UV curing the same sample, a UV curing acrylate adhesive. The intensity was changed here, and interesting is that at a certain intensity, if you increase that, then you do not accelerate your curing anymore, the opposite effect and inhibition occurs. There are various possible reasons for that. Maybe, so it's not exactly known right now, but there are explanations, a couple of explanation possibilities. Maybe too many initiating radicals are generated which encountered and cancel each other. Or another explanation could be that a high exposure may also create excessive amounts of short polymer chains and no long ones anymore. Or it's possible for a bleaching of all photoinitiators eliminates a screening of UV radiations from the monomers, causing them to absorb the UV photons, and then they are too energetic and cannot form bonds anymore. So it's interesting. It offers interesting measurement possibilities. And at the end of UV studies with the dielectrical analysis, you get figures like shown here in that table. You see here the degree of cure, which you can calculate from your curing curves as a function of the intensity of the UV light, of the exposure numbers with the UV light, and the distance of the light source to your sample. In the second part of the webinar, I will show you measurement possibilities with the DSC for curing reactions. DSC is differential scanning colorimetry. Many people know it, but there have been some interesting developments in the DSC measurement technique the last 5 to 10 years, which you can see here on that slide. So the last 50 or 60 years, heat flux DSC, quite big ones, have been used, like shown here on the left-hand side. They have been invented in the 60s, in the 1960s, and they are still in use, but the trend goes to smaller devices, to microchips. And in these microchips is a heater in the middle, which replaces these big furnaces. Then you have a thermocouple here on the upper side, on the sample side, and a thermocouple on the reference side. And the reference itself is included here in that sensor. The specific heat capacity is exactly chosen to compensate here the empty crucible, which you are using, in general aluminum crucible. So you do not need a reference for chip sensors for this chip DSC. Here is the schematic heat flow and the measurements. So the resistance is measured here. So the voltage drop on the sample side and on the reference side. And if anything is happening inside your sample, if you have an exothermic reaction, then it's getting hotter on that side, and a heat flux from the sample to the reference side is bringing that delta T between the reference and the sample again to zero. And what you get as a result are curves like that. This is a typical DSC measurement on an epoxy resin. It shows 2 runs. the first heating run is the blue curve. It shows a glass transition, which is a step here. And then after the glass transition, you see an exothermic peak. And this represents a post-curing. So the sample which was investigated here was not at 100% degree of cure. And the post-curing, after the post-curing, a second run was done, and you can see no further curing. So after the first heat, we reached a 100% cure. And what is also interesting to observe here is the glass transition is shifted to higher temperatures with a higher degree of cure. And the DSC is, as I mentioned already, usually used to investigate or to measure cured materials after the curing process. And with the DSC measurements, you can calculate from the post-curing peak here the degree of cure of your cured material. And it's quite easy to calculate. So you calculate this enthalpy here of the residual cure divided by the enthalpy of the zero cured or of the full cured, and then subtracted by 1, which represents 100%, and then you get the percentage of your cure from this DSC run. The glass transition, as I mentioned, is the higher the percentage of cure is. And you also see here, again, that dielectrical analysis and DSC match perfectly for curing materials. The one method is used during the cure in DEA, and the DSC after the cure. There is an exception for DSC where it is used also during the reaction. The DSC can also be used to monitor UV curing samples. So you can attach a UV light on your cell. Then here are examples of an acrylate adhesive, the same as we measured with dielectrical analysis. And we have here, we used here different intensities of the UV light. And you see here you have a higher intensity and a faster speed of your curing reaction in the blue light compared to the red light, which where a smaller intensity of the UV light was used. So if you have already a DSC and if it is possible to attach a UV lamp, then it's okay to investigate UV curing samples. But I have to say that the dielectrical analysis is or would be the better choice, because with the DSC, you are measuring the heat at the end of the day. And as soon as you bring in UV light, you bring in heat with that UV light. And this is included in your measurement peaks. So you have here an overlap of UV light and your measurement curve. And these effects you do not have with a dielectrical analyzer. It measures the dielectrical property and not the heat, and therefore it does not see the UV light, which is beneficial for UV curing samples. We have good correlations between DSC and dielectrical results. You see here the glass transitions are directly proportional, more or less, to the cure index, which is measured with the DEA. The cure index is the degree of cure in percent. And you see, the higher the cure index, the higher your glass transition will be. You have also a direct proportional correlation between the glass transition here on the x-axis and the conductivity or ion viscosity on the y-axis. So it correlates perfectly, DSC and DEA. And it's possible with the both techniques to characterize completely the curing. The examples here show on the left-hand side the isothermal curing curves of an epoxy resin. The blue curve is for the temperature of 60 degrees, so it was cured at a constant or isothermal temperature at 60 degrees. And you can see after around 60 minutes, it's finished. When you look on the other higher temperatures, you can realize that the curing times are much faster and the degree of cure is also higher. On the right-hand side, the dynamic cure is shown. So the samples have been heated up with a constant heating rate, and you can see also at which temperatures you have final cure or 50% cure. So you get a full characterization or full curing curves with DSC and DEA. So, and last chapter for today is the instrumentations for the DSC. What kind of instruments are available from our side? So for curing processes, we offer 3 instrument models. One is for routine measurements and also for teaching purposes in universities, for example. It's the DSC1 model. It's quite good also for curing processes. The advanced model is the DSC10. It can measure also at sub-ambient temperatures. The one model only from room temperatures upwards. And these are small instruments. The footprint is only 20 by 20 centimeters. So very small instruments. The high-end chip DSC 100 is shown here. It can be equipped with many options. They are listed here. Modulated DSC camera options to visualize your sample during the measurement. UV, you can attach UV lamps like shown here. Low temperature options, sample robot, vacuum, a Raman spectrometer. That's also interesting. The Raman spectrometer, you see amorphous and crystalline parts in your sample. Every 1 second, a Raman spectrometer can be recorded. So that's for the high-end DSC. We have different coolers which can be attached to the high-end DSC. Hang on. It's the Peltier cooling. It goes down to minus 20 degrees Celsius. Intracoolers down to minus 70, or quench cooling with liquid nitrogen down to minus 150. Here is an example of the video chip DSC. So a camera can be attached and then you can record videos. So at the end of my presentation, I want to make a short conclusion of what we have seen. The dielectrical analysis is the only measurement method with which you can see the complete curing reaction. DEA and DSC match perfectly to give you a complete information about the curing process itself and about the analysis of the cured material to see the degree of cure, post-curing, and the glass transition. A broad variety of accessories is available from us as the equipment manufacturer is, you have seen, various sensors for the DEA, also easy and cost-effective sensors for the DSC, presses, parallel plate devices, photo curing, UV lamps we can offer for both instruments, DEA and DSC. The measurement itself are very easy, I would say. The handling of the instrument and the calculation of the result is done more or less automatically by the software. The sample preparation, it's very easy. And the instruments are quite small and light. And last but not least, we offer bundle packages, DEA, DSC, for attractive conditions. So thank you very much for your attention.